Hello and welcome to my solutions to the stats mock. Okay, I'm just doing it. I've done the mechanics mock. I don't know if you've seen that already. I tend to run out of steam when I'm doing these things, so I made an error at the end of the last one. Eventually corrected it, but I was missing a factor or two. So feel free to have a good laugh at that on the last question of the mechanics mock. Okay, let's get on with it. What have we got here? So this is stats. I haven't seen this paper before. Let's have a look at it. I'm making sure I've got the solutions next to me though, so I don't make any mistakes. Okay, so the company is going to survey its customers: new customer, existing customer, service contract, repair contract. I guess these categories are mutually exclusive. They normally are when you set up a two-way table like this. Work out how many new customers with repair contracts should be sampled. So this is a stratified sample, stratified by customer type and contract type. Yeah, so we're going to make sure that these proportions here are mirrored in our sample of 100. First thing we're going to have to do, I guess, is add up all of those. Now, they often tell you what these add up to, but by the look of it, they're not telling you what they add up to. Now, we want to work out how many new customers with repair contracts, well, that's these 82, should be sampled. So that's 82 out of, we need to add all these up, 65 plus 82 plus 231 plus 262. That will find the fraction which we require out of 100. So if we multiply that by 100, that should give us the answer. And if you add all of these up and divide it by that and multiply 100, I think it equals 12.8125. But of course, we need a whole number, so 13 should appear in the sample. Should be sampled. So hopefully that one's not too bad. That's a fairly gentle start. That's just stratified sampling. That's part of GCSE. That really is. Okay, the company collects information. The company has developed a test for a certain fault. Okay, so it's looking for faults. The test sometimes gives incorrect results. That's a shame. So the company collects information from a sample of randomly selected machines. 2% of the machines have the fault. 70% of the machines with the fault test positive. 10% of the machines with the fault test positive for the fault. Okay, yeah. So these are what's known as, look at this sign here. These are what's known as false positives, yeah? You can get, this is a very famous problem in statistics, the problem of false positives and false negatives. It's been put in the spotlight recently because of things like the pandemic and stuff like that with the little tests that they had. It's always been well established and well known that false positives are a horrendous problem for testing, especially if you've got a disease which is quite let's say if you've got a disease which is quite prevalent and you've got a high false positive rate, that can be a real problem. Let's see what this question is getting at. I bet it reveals the problems with false positives. Okay, right. A machine is selected at random from the sample of the machines and tests positive for the fault. Calculate the probability that the machine has the fault. Okay, right, so what are they really getting at here? A machine is selected at random from the sample of machines, and it tests positive for the fault. So that sounds like conditional probability to me, almost like, or this question is definitely going to be about conditional probability. Okay, now we want to find the probability that the machine tests positive, has a fault, given that it tests positive for the fault. So let's just write that. I'm going to write it like this. Find the probability that the machine has the fault, I'll put that as F, given that it tests positive for the fault. Yeah? Now, how are we going to work that out? Yeah, and I hope you can see as well. That's quite often in conditional probability questions they use the word given that. This isn't one of those times, I'm afraid. We can see it's been given though, because given that just means you already know a piece of information, and we know that a machine was selected at random from the sample. And this machine's definitely tested positive. So we know, given that it's positive, and now we're trying to find the probability that the machine has the fault. Well, that would be the probability that the machine is faulty and positive, divided by the probability of what you're given, just positive. Now, how are we going to work out these? Now, this is where we might need a tree diagram or something like that just to help sort of like clear up the question, yeah? If you've got a tree diagram, it says 2% of the machines have the fault. So the probability of a fault is 0.02, yeah? And the probability of not having a fault is therefore 0.98. That's not fault. Okay, and after that, you want to know whether you test positive or negative for the fault, positive or negative. Now it says 70% of the machines with the fault test positive for the fault, yeah? So that's like 70% of the machines with the fault will test positive. So if we do 0.7, yeah, times by 0.02, that should give us what we need here, 0.7 times by 0.02, we get 0.014, yeah? Okay, now what have we worked out here, yeah? In fact, you're better off, I think you'll probably prefer me to put it like this, actually, because otherwise you're going to get confused, that this value is 0.7 because 70% of the machines with the fault test positive and therefore 30% test negative, and it's the other way around, different here. 10% of machines without the fault test positive for the fault. Oh, sorry, so that's 10% and that's 90%. Yeah, so it normally gets it right, but not always. Yeah. Now, what's the probability of being having the fault and testing positive? It's going to be 0.02 times by 0.7. And what's the probability of testing positive? Well, that's this branch and this branch. So it's going to be 0.02 times 0.7 plus 0.98 times 0.1. So quite a tricky question, this, no doubt about it. Let's now work that out. 0.014 divided by 0.014 plus 0.098. Okay, and I'm getting there 0.125. I think that's a pretty tricky question, I'll be honest with you. I don't think that's easy at all. Comment on the usefulness of the company's test. Okay, right. There's only a 1 in 8 chance that the actual test, if you've got a positive result, there's only a 1 in 8 chance that you've actually got the fault, which sounds useless, yeah? Test not very good, as even with a positive result, there's only a 1 in 8 chance of actually having the fault. I know, I always remember when I was teaching a student who was applying to do medicine, and she was doing double maths at A level, and she was asked exactly this question in her interview. Come and speak to me if you want to be asked the same question. I've got it written down somewhere. It's a really good question, and it shows the problem with false positives, and it also shows the problem with medical statistics, having a really good understanding of medical statistics. I'd love to waffle on about that, but this is not the time or the place. Okay, but yeah, come and see me at work if you want to chat to me about it. Okay, when the company services the machines, it checks two components, alpha and beta, for wear and tear and replaces these if needed. Event A is that component alpha needs to be replaced. Event B is that component beta needs to be replaced. So I guess we've got replace alpha and then don't replace alpha and then replace beta. I like to think of things in terms of tree diagrams. Don't replace beta. Ooh. Tree diagrams I think are really useful. Replace beta, don't replace beta. Yeah. Okay, the probability that component alpha needs to be replaced is 0.35, beta 0.55, and therefore that's 0.65 and 0.45. Okay, right. Okay, I've just realised though they're not independent, so this tree diagram is dangerous doing this because actually, okay, the probability that neither component needs to be replaced is 0.28. Yeah. In other words, when they say this, I got a bit ahead of myself with this tree diagram here because this is typical me. I didn't read the question. Show that events A and B are not independent. Well, if we're trying to show something's not independent, we need the independence test. Yeah. So event A is alpha needs to be replaced and event B is beta needs to be replaced. So what we're going to do is we're going to work out. We know the probability of A because look at this, 0.35. Yeah, we know the probability of B. They've told us that 0.55. Yeah. Now, if they're independent, then the probability of A and B should equal. Yeah. Let me just put it like this: if Indy, probability of A and B should equal 0.35 times 0.55. Yeah, but let's try and draw a Venn diagram. They're often really useful in these situations. This is event A, this is event B. Now they told us this was 0.35, they told us this was 0.55. They also told us neither component needs to be replaced as 0.28, yeah? Now remember that means that you now know A or B. And probability of A and B, for all probabilities this is always true, equals P of A plus P of B minus P of A or B, yeah? You can always use that result, whether independence holds or anything else. And so if I just use this to find the and, because I've got 0.35 plus 0.55, is that? Minus, now A or B in this diagram is just going to be 1 minus 0.28, which is 0.72, yeah? And that gives me, let's have a little look, 0.35 plus 0.55 minus 0.72, 0.18, yeah? So I now know the middle is 0.18. And that's all I need to know, yeah? These are not independent, yeah? As P of A and B equals 0.18 and P of A times P of B equals 0.35 times 0.55, which isn't 0.18. Let's find out what it is. Oh, my calculator keeps turning off as well. Low batteries. It's going to be tough getting through this. Equals 0.1925. Hence, they're not independent. Yeah, there's also, I can't spell independent. I'm spelling it like I'm an indie music lover. Okay, right. Not independent. Right. Okay, so that's that one done. Okay, find the probability that component A or component B needs to be replaced, but not both. So, right, that will just be 1 minus, well, basically 1 minus everything, 1 minus 0.18, because we want to find the probability that either A or B, but not both. Yeah, so if we can just write this down here, basically we want, let's just write these on the diagram now. Let's get rid of that. That's kind of confusing the way I drew that diagram. I often will write down, oh, I've lost connection as well. This is definitely not good. My phone's going, I've lost connection. I often write down on the edge numbers when I mean both the circle, the out, the half moon, if you like, the crescent moon, and the oh God, this is really annoying. Okay, so if I now subtract anyway 0.18 from 0.35, I'm going to get 0.17. And here 0.55 minus 0.18 is 0.37. And so if I want to now find the probability that A or B needs to be replaced but not both, I just need to do 0.17 plus 0.37, which equals 0.54, I think. Cool. Hopefully that was useful. It's quite a tricky one, that one. That's not an easy question by any means. I can see why you found that one tough. Okay, question 2. Wow, we've got 5 more to go. I may have to stop this video here and do this in 2 parts, but I'm really reluctant to. But it is dinner time, so I'm going to stop it. Okay, back to do yet another stats question. Let's have a go at the second one then. Right. I'll probably only get a chance to do a couple more, but what do you care? I've got to take my daughter to Kids Kingdom in 20 minutes, but let's see if we can get one more done. Okay, partially completed table adds up to 120 job applicants. These ones, they like these questions. A histogram is drawn. The bar representing 5 to 7 has width 1. I find it really helpful to have drawn the bars here. So 5 to 7 has real width 1 centimetre and height 5 centimetres. Obviously, that is an area of 5 centimeters squared, and that represents a frequency of 10. Yeah, in other words, double the area to get to the frequency. So 14 to 18, well, firstly 14 to 18, the width should definitely be 2 centimeters, as a gap of 2 is 1, a gap of 4 will be 2, and it has a height of 4 centimeters. Yeah, so that's going to be 8 centimeters squared. So this is quite a nice one, really. And so it represents a frequency of 16. And now we can show the work. Well, now we can find this one as well, can't we? Because it adds up to 120. That's 33. That's 84. That adds up to 100, and so that must be 20. And so now, showing you're working, estimate the mean time taken for the 120 job applicants. Well, we're going to obviously be doing our standard way of finding the mean from a table, which is x bar equals, we'll need midpoints, 6. Now, what's the middle of 7 and 10? It's 8.5. 12, 16, and middle of 18 to 30, and it's continuous. Well, that's going to be add 6, 24. Yeah, so we're going to need to be doing 6 times 10 plus, you need to show all of this, 8.5 times 23 plus 12 times 51 plus 16 squared plus 24 times 20. And then we're going to be dividing all of that by the sum of the frequency, which is 120. And that comes to, it's easy to make careless errors on this, but try not to. But it should come to 13.4 to 1 decimal place. Okay, so those two quite nice starts to the question, really. This should be a nice question. The lower quartile of the times is 9.6 and the upper quartile is 15.5. I presume they've done that by interpolation. You could actually work that out yourself by interpolation, but you don't need to because they've told you the answer. For these data, an outlier is classified as any value greater than, well, more than 1.5 IQRs above Q3. Okay, right, so showing your working, explain whether or not any of the times are outliers. Well, we need to do. So we need the upper quartile, which is what we've got. We also need the interquartile range. So 15.5 minus 9.6 is the interquartile range. I'm timesing that by 1.5, and I'm adding on the upper quartile, 15.5. And what does that come to? I'm just going to use my calculator. It comes to about 24.3, 24.4. I don't know why it's giving me two values there. My calculator at the moment is really running out of battery, but let's see if I can finish the calculation before it turns off. No, I believe it's 24.3, 24.4. Now, if we go back to the table, this goes up to 30. So it appears that there could well be outliers. There probably is. There's a high chance of outliers. Probably some outliers as the final class interval goes up to 30. Outliers as our table goes up to 30. As the last class interval goes up to 30. So this is significantly easier than the first question we did. Okay, estimate, right, candidates with the fastest 5% of times are for the task are given interviews. So these candidates, basically, the assembly distribution. Estimate the time taken by a job applicant below which moment be given an interview. So this is interpolate. This is really interpolate. Find the top 5 percentile or the 95th percentile, if you prefer to put it like that. We want the fastest 5 percenters, yeah? Now, what is 5% of 120? Is, well, 10% of 120 is 12, so 6, yeah? So we want to find, if we interpolate, roughly what 6/10 of that interval is, yeah? So if we do 6/10 and times by the width of the interval, which I think is 2, because it goes from 5 up to 7, and then just add on 5, because the interval's starting at 5, we should have our answer. 0.6 times 2 is 1.2, plus 5 is 6.2 minutes. And I think any time under that should be, yeah, that's 6 minutes and 12 seconds. I don't think they want it in minutes and seconds. But yeah, any time quicker than that, and you get a job interview. Cool. That was quite a nice one. I know this one isn't nice, though, because I did it in class and I thought, yeah, this is pretty tricky. Okay, 2 events are mutually exclusive, so that's nice. We've got to draw a Venn of this information, yeah? If they're mutually exclusive, they don't overlap. And we also know that P of A, so if we call this A and B, this is P of A. Oh, but it's also 3P of B. So if I call this P of B, we can just write it equals 3P of B. Or even more clearer, let's call this one on the right-hand side X, then the left-hand side one will be 3X. Yeah, Okay, right. Find the possible values of P of B. This is a bit of a weird one, really. I don't really approve of this question, but my approval is really irrelevant. Oh, P, I did something I've just missed. It says P of B equals P. So why am I using X? I should be using P. P and 3P. Yeah. Now, find the possible values of B. Well, firstly, the probabilities have got to be greater than 0. Yeah, it doesn't equal 0. So P, P is definitely going to be greater than or equal to 0. But you also know that 4P must be less than or equal to 1. In other words, P is less than or equal to a quarter. So that tells you that 0 is less than P, which is less than or equal to a quarter. It's almost so simple it catches you out, that question. That's the way I put it. Okay, that's a range of values of P of B, though, which is, of course, P. Okay, two events C and D are such that probability of C given D equals 3 times probability of C. Yeah? Explain whether C and D could be independent events. I don't think so, actually, because probability of, well, firstly, there's two definitions of independence. We heard one earlier, A times B equals A and B is one definition of independence. But here's another one. Probability of C given D equals the probability of C given not D equals P of C, yeah, if C and D are independent. Now, this has a really nice intuitive understanding because what this is saying is if D has happened or not, P of C is still P of C. Yeah, doesn't matter if D has happened or not, P of C is still P of C. And we really only need the middle, the first and last expression. We only need this. So it don't matter if D has happened, probability of C given D is still P of C. Now, because of that, look at this. If P of C doesn't equal 0, there's no way probability of C given D can equal P of C if probability of C given D is 3 times P of C. And hence, they're not independent. Guaranteed. They're not independent. Okay, right. Last one. What have we got? Now, this is a hard bit. This is a really hard bit. Definitely. Okay, right. We've got probability of C and D is a half. Okay. And this is the kind of question where you end up scribbling things out and changing them and all that kind of stuff. And the probability of not C given not D is 7/10. So this is 0.7. So I've just realised this says a half P of C. Yeah. Now, remember as well, this says given also that. In other words, this initial claim is also true. Yeah. So we know that probability of C given D is 3P of C. But remember that this is the same as probability of C and D over D. Yeah. In other words, let's rearrange this to see that the probability of C and D is 3P of C, P of D. Now let's mess around with this one because we also know that the probability of C and D is a half P of C. Yeah. Well, that means I can plug this in here and say a half P of C equals 3P of C, P of D. Didn't finish that bracket off. Okay, we can cancel the P of C's, yeah, and we can now work out P of D to be equal to 1/6. That's a great start, that really is. We know all of that is 1/6, yeah? That's what we know. Now, we're going to have to fill this whole diagram in, yeah, and we're going to have to do it very carefully. Now, let's take that off as 0.7 because we've got a sixth here and we've got like 7/10 there. I'm starting to think 60ths would be a good idea to work with just because I'm not going to be able to use my calculator because the batteries run out. Okay, so 7/10 is the same as 6/7 of 42 out of 60. Yeah, and we know all of this circle is 1/6. Yeah, well that means like if we add 1/6, which is of course 10/60ths. Yeah. And we know all of this circle is 1/6, 10/60ths, and that's 42/60ths. That adds up to 52/60ths, and therefore this is 8/60ths just here. Yeah. And now what I can do is I can use some of my results, which I've already got, to find probability of C and D. Because if I write down now, let's call it like X, yeah, then this can be 10/60ths, and I mean 1/6, yeah, minus X, yeah, and I can make sure now, I think these probabilities will add up to 1, so I can't use this, that they sum to 1, but I can certainly use this equation here, that the probability of C and D, which is, let's just use it down here, X, That's going to equal to a half times x plus 8/60, because that's P of C. Yeah. Okay, right. Now we can do it. So 2x equals x plus 8/60. In other words, x equals 8/60. And sure enough, we have this as 8/60. Let's write that on. And therefore this is going to be 10/60 minus 8/60, which is 2/60. Yeah, and you're better off not cancelling down in this situation. And now let's just check that this all makes sense. C and D is a half P of C. Yep, that's good. This is indeed 1/6, and this is looking like 7/10. So it looks right. And hence, P of C equals 16/60, which is 4/15. And it's done. That's a hard question, that. I think that's really, really tough. Okay, let's see if we've got time for another one. I'm supposed to take my daughter out at 5:45 and it's 5:35. I've got 10 minutes. Okay, uniform distribution. Yeah, people forget about this. It's a tiny bit of the course. A uniform distribution is any distribution, a discrete random variable, where the probabilities are all the same. The classic example being a dice. Yeah, 1, 2, 3, 4, 5, 6. Yeah, if the probabilities are all the same, then that's a uniform distribution. Well, this is a fair five-sided spinner, so this should have probabilities of a fifth, and that's a uniform distribution. Yeah. Okay, the spinner is spun 28 times. Right, now we're looking at a binomial distribution, I reckon, because we're spinning it multiple times, and this represents the number of times it lands on to. Yeah, so x is binomial. 28 is the number of spins. Probability of success, 1/5. Find the probability that the spinner lands on 2 at least 7 times. Okay, right. Well, what do we need here? We need to say we're looking for the probability that x is greater or equal to 7, but your calculator only does less than or equal to. Now, 7 or more, what's the opposite of that? 6 or less. So this is x is less than or equal to 6. If we do 1 minus that, we should have our answer. You can type it in on a calculator. You get 1 minus 0.6784, and that's 0.322. Make sure you're good with the calculators for those ones. It's a really good idea. This is really saying I prefer to work with less than or equal to's when I see something like this, because I think they're less confusing. Now, if you want to work out the probability from 4 to 7, you can work out the probability that x is less than or equal to 7 on a calculator, and then subtract from that the probability that x is less than or equal to 3, because that would leave you the probabilities 4, 5, 6, and 7. Because you would have taken off 0, 1, 2, and 3. And that comes to 0.818 minus 0.160, and that is 0.658. Cool. Oh, we did that in a couple of minutes. That wasn't too bad at all. Have we got time for one more? Or both more? It'd be nice to finish it. Okay, right. What do we got here? Right. Using your knowledge, he's investigating the total rainfall in May. Okay, yeah, this is total rainfall. You've got to remember, in the total rainfall column, they've got trace amounts, yeah? And so this is why he needs to clean the data, because there's some entries in the data set which just say TR. TR is in the data set and needs to be either ignored, or you could just reduce it to 0, or a very small amount, or reduce to 0. Yeah, so you've got to clean the data because you've got some non-numerical entries. That's the problem. Traces in the data set, and it needs to be either ignored or reduced to 0. I prefer probably reducing it to 0 because it's trace amounts. Okay, using the information from the large data set, he's got this table. Okay, interpolation. They want us to interpolate. We've already done a little bit of interpolation, but let's do some more. Okay, what's the frequency add up to here? 131, 155, 167, 184, I think, yeah. let me just check that. Did it actually say in the question that he's taken the 184 items of data? Probably not. That's slightly annoying because you will need to add up the frequency then there. And so let me just check I've added it up correctly. 131, 155, 167, 177, 184. Yeah, it's 184. Okay, so right, we want to estimate the interquartile range. Okay, where's the lower quartile going to be? It's going to be 1/4 of that, 92, which is 46 item of data. Now, where is the 46th item of data? Well, it's somewhere in here. So we need to do 46 over 121 multiplied by the width, which is 0.5, and then add on 0. Yeah, and so that's going to give me what Q1 equals 0.190. Upper quartile, well, if we times this by 3, we're going to get 120 plus 18, 138th item of data. Where is that? Well, that's 131. So it's going to be the 7th one out of those 24. And so we need to split that interval up, which is a width of 4, into 7/24, and then add on 1. And 7/24 times by 4 plus 1, I think that comes to 2.17. Now we just subtract. IQR equals 2.17 minus 0.19. And that is, I think it comes to 1.98 if you round it carefully. Yeah. You're probably better off using the exact values here. I've rounded them. This one was like 2.1666. But yeah, I think finally, if you work with exact values, you should get an answer which is rounding to 1.98. Okay, calculate an estimate for the standard deviation of the daily total rainfall in Herne from May to October in 2015. Okay, this you can do completely on your calculator, or you could use the summary statistics. If you're interested in the summary statistics, it would work like this. Sum of fx squared, which is this one, divide that by the total frequency, minus this divided by the total frequency squared, because it's the mean of the squares minus the square of the mean. All of that squared, yeah? It's nice to know that formula, or you can just use your calculator, yeah? And that's 5.77. Cool. State the assumption involved with using class midpoints to calculate an estimate of the mean. So you use midpoints, you're assuming data is evenly spread throughout the interval, yeah? You've assumed data is evenly spread throughout the interval. And that should get you the marks. Let me see what they said in the mark scheme, actually. They said that the data is uniformly distributed, which is exactly the same thing. Okay, using your knowledge of the large data set, explain why this assumption does not hold in this case. Well, I mean, this is really unfair, I think, but if you know that column well, most of the values are 0 or trace. So this assumption is unlikely. That's harsh, though. That's where I genuinely feel for you on the large data set questions. State giving a reason whether you'd expect the actual mean daily total rainfall to be larger or smaller than the estimate based on this. It's likely to be smaller since the first group has more zeros. Yeah, so it's all about knowing that column in the large data set here, which is a pretty a big ask, really. But yeah, have a look at large data set. There's a really good website actually called Westie's Workshop, which has some really good large data set stuff. Okay, right, what we got here? Turn a Venn diagram into a tree diagram. That's quite interesting. Okay, so probability of A, by the look of this is going to be, well, all of this. Now, that's 6/15 plus 4/15, so that's 10/15, yeah? And so not A must be 5/15. So in other words, that's a 2/3 and a third, yeah? Now, this is where it gets a bit more difficult because well, it's sort of difficult, but it's not. On a tree diagram, you actually have conditional probabilities on the second branches. This is a probability. What this says, it says B, but this is probability of B given A. That's actually how we do tree diagrams. Now, what is the probability of B given A here? Well, the probability of B given A is really just probability of B and A divided by what you're given, A. In other words, if I want to find this, I need to look at 4/15 and divide it by 2/5, which is of course 6/15, and 4/15 divided by, oh sorry, and I said just this, I need to look at all of this. I need to take 4/15 and divide it by 10/15, and 4/15 divided by 10/15 is 4/10. Yeah, that's subtle, that is. It's because on the branches we actually use conditional probabilities. Really very subtle. Therefore, this is going to be the opposite, 6/10. Same down here. This is really not a, if I can write it down, this is probability, let me cross it out and say it's probability of B given not A, which is obviously B and not A divided by not A. Well, what is that? Well, not A is a quarter plus a twelfth, so that's 3/12 plus 12, that's 4/12. We'll just write these down to make it easier for us. What's the probability of B and not A? It's just a quarter, and so that's 3/12. And so I think that's going to be 3/4, and therefore the last one is 1/4. Yeah, I like that question in terms of what it's teaching you. I really do. I think it's an important fact to learn that conditional probabilities exist on tree diagrams, on the second branches and all subsequent branches. Anyway, I better dash because I've got to go to King's Kingdom. Hope you enjoyed the video and found it useful. Anyway, maybe enjoyed the wrong word, but hope you found the video useful. Come and ask us if it's still confusing, my explanations. They probably are. This is quite a tough mock. It really has to be said. It's a tough mock. Okay, well done though. Bye bye.